Okay, well, I'm really happy to introduce my long-term colleague and friend, Hagit Messer from Tel Aviv University. I first met Hagit, we were trying to figure out when we first saw each other, probably 85, when we were—
One of you were not born yet.
Yeah, we were supported by the same grants through our advisors, postdoc advisor and my thesis advisor on bearing estimation and time delay estimation. Peter Schultheis and Stu Schwartz were respectively involved with that. So we've known each other ever since, and we've seen each other at many conferences and many different venues. She has lots of awards. I won't be able to go through all of them. Just suffice it to say that IEEE Life Fellow, and she has some paper awards, and she's now emeritus, right, at the university.
1 month.
1 month, yes. So congratulations.
Thank you.
And she's been chief scientist at the Ministry of Science in Israel. She's been a real policy oriented stint at both the university and government. Was president of the Open University in Israel. So we're really delighted to have her speak about very exciting work that she's been doing, applying signal processing, statistical modeling to environmental sensing problems. Very valuable for both society and science. So, Hagit.
Thank you all. Thank you all. Thank you, Shelley. Actually, I'm here for 24 hours and I enjoy it a lot. As Al said, over the years, he always say, you should come, and then I decided to come, and I will come again. So, because you were so great. Actually, as Al said, we have a similar background, but in the last 15, 16, maybe 17 years, my research, I put together everything I did on some specific applications, and I'm going to scan 15 or 16 years of work today, which is a lot. So last night I cut my slides by half, and I'm not sure if I managed not to make it too dense. I decided to put everything in one slide. So here it is. At least you get the idea to start with, and then I hope that the rest will come later. I will not go deeply into what I'm showing, but I'll give you the hints where to find more if you're interested. So the specific problem we are talking about is environmental monitoring based on measurements from commercial microwave links. So we don't use designated equipment, but since the electromagnetic signals, which is used in wireless communication, is affected by the propagation media, and the propagation media is the atmosphere, then in a way, in it you can find tracks of many environmental phenomena. And what we do is kind of inverse problems. And that's what we do over the years. Actually, it all started, as I said, in 2004 and 2005. This plot in the right is the one that you get from the ITU. When you want to build your own communication system, then you need to consider the effect of weather, and in particular rain. So the people who design communication network, they are familiar with this plot. On the x-axis, you see the frequency of the electromagnetic wave. On the y-axis, you see the anticipated attenuation in dB per kilometer. And it was used for designing communication networks. And our idea then was to do, as I said, the reverse engineering, because the frequency of the signal is known, and all the modern communication system measure and log the signal level. So you know the y-axis, you know the x-axis, and then you can tell about, for example, the rain level. Very simple idea, but nobody used it before. And what I'm going to do is to go over what we did over the years, but to put it in the framework of opportunistic integrated communication and weather sensing. Oh, okay. So my talk will be put in 3 parts because everything is put in 3 parts, right? And the first one will be introduction, which will kind of overview of this technology. We use the term CML, meaning cellular environmental monitoring technology. So I overview it and I will present it as opportunistic integrated weather sensing and communication. And then in part 2, I will focus on its relation to signal processing from both directions. One direction is how do we use signal processing to improve results of the environmental monitoring, and the other direction, which is in a way more interesting, is the kind of theoretical signal processing problems that come out of these practical problems, which is the fun of being academicians. You can do whatever you want, and if it is interesting, who cares about what you do with it, right? And in the last part, I will try to share with you some of the general lessons that I got from this experience. So I'm sure that you are all familiar with this new emerging term of ISAC, integrating sensing and communication. It's everywhere now. Actually, when I started to prepare this talk exactly a month ago, I checked, for example, how many times this term, integrating sensing and communication, appears in Google Scholar. So at that time, it was almost 700 times, 500 out of them in the last year. Now I checked today, a month later, and it was already 815. So it's dramatically increasing. Then I also checked the website of IEEE, and there were more than 400,000 results. And in the Web of Science, there were not so many, only about 40, but as you can see, 30 out of them from the last year. And they are all under telecommunication, engineering, electrical and electronics, computer science, this is it. So it's a very hot topic, okay? And what are we talking about when we say ISAC, integrated sensing and communication? And this figure I took from an overview of this technology. Actually, instead of talking about cellular communication, where we had here a base station that controls the communication with the cell, with the handset, etc. Now the base station is replaced by smart gateway. Everything should be smart right this, right? So now it's a smart gateway, and this smart gateway integrate different technologies, different signals. We have ISAC signal, we have communication signal, we have sensing signal, everything on one tower, and the technological challenges come from the fact that you want to eliminate interferences between different signal, different technologies, and you want to do it in efficient ways. So this is the emerging technology, and they say that in the 6th generation, this is what we are going to face. Actually, as I said, the IEEE community is very much into ISAC, and there is a nice webinar series on ISAC, which is jointly organized by the Communication and the Signal Processing Societies. And last week, on November 4th, there was a talk by Marco Lopes, and he was focused on a special case of ISAC, when all the different technologies, sensing and communication, use exactly the same frequency band. So there, the challenges are different. And he proposed to distinguish between 2 types of such ISACs which use the same frequency band. One which he called a joint sensing and communication. So you can call it J-ISAC, meaning that you design your communication system to share the same frequency band. So you can use different technologies like time, division, et cetera, for sensing and communication. So this is joint. It is planned, designed to coexist. The other direction is what he also referred to as opportunistic ISAC, meaning that you have technology for one purpose, sensing or communication, and you also use it for the other function. And what I'm going to show you is that what we do over the last 15 or 16 years is actually opportunistic ISAC, because we used the communication signal for sensing. And actually, my approach over the years was to be very passive, not to change anything in the communication signal, but to compensate for the non-optimality of the signal by smart signal processing, okay? So I will, as I say, overview of what we did from 2005. As you can see from this figure, that's how cellular communication systems were there. You see, you didn't have yet smartphone, so that was the kind of handset. And I want to emphasize that at least at the beginning, our focus was on the signals between the base station, which is the backhaul of the cellular network. And the backhaul of the cellular network can be either by wireless signals or fiber. In many countries, like in China, right from the beginning, they put it underground. But in most European countries, it is still on microwave links. And the advantage of using these links is that it is point-to-point, line of sight, and the only thing which affects the signal, the physical property of the signal, is changing in the atmosphere, in the environment. So this is the simple way. If you use other channels, like the mobile channel, the fading may be caused by other effects, like moving, like going indoor, outdoor, etc. So we started with the simple challenges, where it was only a matter of the propagation media. And this plot, which I showed you before from the ITU, this is an extended version. Again, I have frequency on the x-axis, and you see this, I don't know, is it gray? Gray area is the K-band frequency, which was used by a backhaul network till the third generation of cellular system. In the fourth generation, we moved to E-band, which is this area. And here again, on the y-axis, you have the attenuation in the signal in dB per kilometers for different environmental phenomena. The blue lines refers to rain. If the rain is stronger, then the attenuation is larger. The green lines refer to fog, and the dense fog causes more attenuation. And these orange lines, this one refers to absolute humidity, the water vapor in the atmosphere. And the other one with the peak at 60 gigahertz is just the oxygen. You may be familiar with the fact that 60 gigahertz is the cheapest frequency band because of this attenuation. So we see that the information is there, but there are signal processing challenges, how to extract this information from the measurements. As I said, the idea came to us back in 2005, and we submitted a paper to Science magazine, and it was published in 2006. It was a Brevia, a very short paper. Actually, it was amazing how simple it was to publish in Science. This is a different experience to electrical engineers. It's different from publishing in IEEE. But we got real data from cellular providers in Israel, Cellcom, and we have shown in this paper that we can actually transform such a link that we see here into a virtual range. Yes, please.
So on the previous slide, you said that you can't use like underground cables for this sort of sensing. Is that because they're shielded well enough that like there's no interference?
Yeah.
Or is it that like there's nothing worth analyzing like on the ground?
No, because they are shielded and we were interested in the atmosphere. Actually, people were thinking, and we were talking about it at the beginning, maybe you can use the following the underground signal to detect earthquake. But this is a different phenomenon. I'm not talking about it today. So this paper actually attracted a lot of attention for the media. For example, this was in New York Times at that time, because the science journalists, they like weather, they like communication, cellular communication. So it really opens a new direction. And I must emphasize that the idea to use a point-to-point communication, not communication, point-to-point signals to measure rain was not new. The physics was there many years ago. And there was a European project back in the late 90s. The European community supported such a project to build such infrastructure to measure rain. But our idea was to use it opportunistically based on communication signals. And why is it so attractive? Because look at this. This is what you already have. For example, France is covered by such links, okay? You see Sweden here and the Netherlands there, and here is Israel. In Israel, I never put borders on my plots because I don't want to get into political issues. But you see that it is heavily covered by such links. And actually, I can tell you there are about 10,000 such links, commercial microwave links over Israel, where we have only less than 500 rain gauges, official rain gauges. So the scale of data that you can use using this technology, the scale of measurement is much higher than what you have is designated near ground measurement facilities. And again, I want to emphasize that when you look at a communication tower like this one, in Israel, it is messy. Here it is better. I looked when I drove from the airport and I saw that it is nicer, but in Israel, it is always messy. I'm talking about this antenna, the round antennas, which are used to communicate between the towers. These are the links. The other antennas are used to communicate with the handset. So we have this, and we started with this application bottom up, and over the years, it interacted with some signal processing issues. Like, for example, when we started, the first thing was sensor network. What we have here is a sensor network, right? And then the big data came. And we do have big data of national and international, if we want to talk about weather. And then IoT came along. And what we have here is definitely IoT. And now the new wave is ISAC. So we have opportunistic ISAC. So we always interact with the new emerging buzzwords, if I may say. Just to give you an idea, what are we dealing here with? In a given area, like this area here that you see on the Israeli map, we have several links. The density depends on the environment, if it is urban, suburban, or rural. Of course, in urban area, the density is high. In suburban, it's medium, and in rural, it will be less dense. And then in a given area, we have several links. They are usually in different frequencies, different lengths. And from each of this link, we get a time series. And here is an example of 8 different time series from 8 different links. And usually each links give us 2 signals because these are one this direction and the other this direction. We have a receiver and transmitter in both sides, and they are in different frequency. Here the x-axis is the time, and the y-axis is the received signal level in dB or dBm. And you can definitely see that when the rain comes, there is attenuation here. But you can also see the signal processing challenges, like the dynamic range differs in different links. If the link is long, then the attenuation may be up to 40 dBs like here. And if the link is short, it may be only like 2 dB, okay? And you see that we have quantization, the signals are quantized, and it's sometimes difficult to find the zero level of the signal like here. And you don't know what fluctuation is due to rain or to other effects. So there are several challenges here, but the basic idea and what we could do very early, and it was not done before, just because we had such a variety and the number of sensors that we have, is to build a two-dimensional rain map bottom up. Okay, from the sensor that we had on ground, we could build a rain map. And here is an example. Here, the running video is the first example that we created a high spatial and temporal resolution rain map in a limited area, which happened to be the cluster of the radar in Israel. On the right, you see how the radar moves, and on the left, you see on the same rectangular here, our map. And I must say that when we first presented this map to people from environmental monitoring, meteorologists and other, they were excited like, oh, come on, how do I go back? Back, previous, okay. They were very excited because they could never before see very local events. Like here, you can see this is 1 minute, the temporal resolution in 1 minute. And sometimes in 1 minute, you have very strong rain in a 1 square kilometer pixel. And they couldn't see it. They had some theoretical proof that it may happen, but they never saw it before. For them, it was like biologists seeing first time through an electronic microscope, bacteria and other effects. Because this enables us to get to very high resolution two-dimensional maps. So now, okay. Now, what we can get out of this technology, first of all, if we look at the designated weather monitoring machine, the most commonly used is the weather radar. But if you look at this map of coverage, global coverage by weather radar, so developed countries like the United States and Europe are well covered by weather, by radar. But if you look at developing areas like Africa, it's dark, no coverage. Our technology, which is based on cellular coverage that you can see here on this map, and you see Africa is covered by cellular communication, then it can enable better coverage of weather monitoring in areas when you have no other technologies. This figure here shows you the coverage of rain gauges. It seems to be very good, but the density here is very low. As I say, in Israel, we have like 500. So there are rain gauges everywhere on Earth in rain stations, but the density is extremely low. And usually events like rain are localized, and you miss many of them by this coverage. So the other technology can bring in better coverage. And also, if you already have coverage from other technologies, then we are talking about fusion of different sources of measurements. And as signal processing expert, we know that if you have more data, you can do better, okay? So I don't go into this technology or what is the state of the art of this technology after 15 or 16 years. The main application area is meteorology and hydrology. These are the communities which are interested in the results. This application that I show you of two-dimensional rainfall near ground retrieval is the major one that most groups, most research groups, most around the world are interested in it. So it's now in the level of proof of concept. For example, a group from the Netherlands, they produced a country size RAN maps bottom up from commercial microwave links over a few years. So it's kind of operational, and it is on the level of proof of concept. As I said before, you can also observe other than rain monitoring, like humidity, fog, even dew, and other precipitation, snow and sleet, and also indirectly pollution. And there are, I work with other components, which are not on a proof of concept level, but a feasibility demonstration. And again, I don't have time to go into it. I gave some reference here, and you can follow it because there are interesting questions related to this. Actually, pollution is one thing that I discussed with Laura today. The effect of the pollution is not seen by our signals because it is almost negligible in these frequencies. But indirectly, what we could detect is a low inversion level, which actually tells you that the pollution is trapped in an area. So that's what we have here. So I present here work of my research group at Tel Aviv University. And just to tell you how it works, we have interdisciplinary or multidisciplinary, you should tell me what is the difference between the two terms, a group in Tel Aviv University. And it is quite unique because it is led by us, by signal processing person, but it is in a strong collaboration with a person from environmental sciences, because we need the background in the physics of the problem. So Pinchas Alpert is a co-PI on this project. And now we have a new leader in the group who used to be a student in our group, and he came back as a faculty member. Over the year, we get measurements from cellular companies in Israel, and these are the companies, Pelephone, Cellcom, and PHI. And we are also in close connection with other companies that produce the equipment, the receivers and the transmitters, because there are some technical questions. And in the last 2 and 3 years, we started to get also data from a smart cities operator, which is not the cellular. It's a designated smart cities equipment. And what we do in the university, we put on our academic hat, and we come out with research results, graduate student publication, conferences, some patents, national, international collaboration. And it's a lot of fun. I just want to mention our most recent paper, in which we actually show that we can detect, and here is the ROC curve, migrating birds by looking at the signal and fluctuation in the signal. And this is a potential for using opportunistically this technology to monitor birds' migration. Now, as I said, we started when the cellular communication was in the 2nd and 3rd generation. Now we are up to the 4th generation, looking at the 5th. Yes, please.
How willing are the cellular providers to give you this data?
That's a very good question. And this is one of the challenges. You need to approach them. And in Israel, it was quite simple because the data that we use is a physical measurements, no privacy, no problems with propriety. And this is the data they already have because they keep it in their management network systems. So they give it for science, not on real time, they just share it with us. But if you want to commercialize it and you want to rely on this data, this is a different challenge. Okay, I need to go back again. And I want to mention that when you have 5G, then you have new challenges but also new opportunities. There are many new potential microwave and millimeter wave links, like look at San Francisco or other 5G here. And it's all in E-band, which is nice because E-band is more sensitive to fog and others, but the links are shorter. And with short links, we have more uncertainties because the signal to noise is not as great. And we started to look in these new opportunities. Also in 5G, we have not only received signal level information, but also phase information in the MIMO system, which also carry information about the signals. And we already have a few papers dealing with 5G measurements. And this is interesting first paper regarding the relation between latency in such E-band links and the humidity, and absolute humidity in the air. So we got data from a private company of the latency over 50 kilometers. Sorry, I need to translate it into miles. So maybe it's about 30 miles. The link, this is cascaded 5 links, and we got measurement of the latency, point-to-point latency over a few years, and we got estimates of the humidity, absolute humidity. The ground truth here is in blue, and our estimates, they show a good correlation depending on the prior information. And another emerging topic, which goes into the same concept, is estimated rain from satellite communication, not a ground level, but a satellite. And this paper, which was just accepted for publication, it is going to be published in the IEEE Internet of Things magazine. We looked at measurements, it's in K-band, so it's the same frequency band, but it is for designated IoT terminals from peripheral areas where you don't have good connection, and you just put such cheap terminals, and you can also use it opportunistically for rain monitoring. So this is the end of my introduction, like half time, and let me go through the second part. So
just a quick
yes, please.
So with the satellite application, you could go beyond just rain and fog and vapor, right? You could look at ionospheric effects, right, on the propagation path. So solar flares, which we talked about earlier, create ionospheric disturbances, which generate lots of ionized particles, and presumably the trajectory path.
This is absolutely true, and maybe we can discuss it later. But first, we wanted to cover better the rain everywhere.
Yeah.
And this will, in a way, enlarge the coverage. Actually, the challenge is that even so, the link is very long from the satellite to the ground station. The relevant part is up to the level of the cloud.
Yeah, right. So it's,
and so you need to have some information about the cloud level. So it's not trivial, but it is doable, and it gives you more information about when. And this is especially important in developing countries. When actually you may get a flood in Burkina Faso, and you have no way to predict it because nobody look at what's going on there. You may have a satellite going over it once or twice a day, and that's it. So it's an important challenge. Okay, so let's move to some signal processing.
there's also GPS, right, which you haven't messed with.
Yeah, but this is much lower frequency.
Yeah.
So it carries out a different kind of. But again, once you start thinking opportunistically, the sky is the limit, virtually. So this is a typical signal that we get from all the signal providers. You can see here again the received power level and the time. And the simplified model for that the attenuation, the difference between the received and the transmitted signal is as follows. It has when you look at it in dB, in the logarithmic scale, it has the following components. The first component is the pass loss, which is actually DC, okay? Then you may have or you may not have a component due to precipitation. This is the attenuation that we see here, okay? Then you always have a component due to water vapor because humidity is always there. It may be high, it may be low, but it affects the attenuation. Then there is an interesting effect of wet antenna. If the antenna gets wet, then you get additive attenuation. And on top of it, we have additive noise because of the equipment. And the measurement that we get from the cellular providers are always quantized. So now we translate everything into signal processing challenges. What we have is diverse multi-sensors, which is a great asset in signal processing. We have many sensors, different frequency on the same area, different location, different frequency, different lengths, and diversity is a great asset for signal processing. And then the question becomes traditional signal processing question, like detection to decide if there is precipitation in this signal or not, okay? There is a problem of classification, what kind of precipitation we have. There is a question of estimation, what is the rain rate level, source separation, and then we need to look at accuracy, robustness, complexity of the algorithm. So it's like a playground for signal processing experts. Great fun. And that's what me and my group, we do over the years. Of course, it's not only us, I give credit to other colleagues. But here is how we started with a model-driven algorithm. We did kind of a three-type classification algorithm, starting with measurements of the received signal level and transmitted signal level that we got from the cellular provider. This is an example when we came up with a statistical test, multifamily likelihood ratio test. Do you know this paper by Kay? We used it for this, Stephen Kay. So we used it to distinguish between precipitation and other atmospheric phenomena. And if we did recognize that we have precipitation, then at the beginning we use pattern recognition classification algorithms to distinguish between rain and other types of precipitation. And then when we talk about rain, then we go into two-dimensional mapping, et cetera, et cetera. If we decided there is no rain, then we apply GLRT to decide if we have only water vapor, meaning dry, because that's meaning that we have nothing else, or we have fog or dew, which actually integrated into moist or wet antenna, if the humidity is high. So these are a classical signal processing approach, but as all our community, we needed to move into data-driven algorithms. So in the model-driven algorithm, we had kind of physical model like this simplified model, which relates attenuation and rain rate. This is the basic equation, which say that the attenuation in dB is a power law of the rain rate, where L is the distance between transmitter and receiver, and A and B are two coefficients depending on frequency, polarization, and the climatological characteristic of the signal. And this or other physical models are replaced by labeled data. Straightforward, and we have published our first paper where we use the LSTM to classify between a wet and dry period. In a way, using data-driven methods, we converted this link into virtual rain gauge. And actually, it was nice because we trained the same algorithm with data in Israel and Sweden, which are different climatological area. And when we trained it in Israel and validated in Israel, we got very good result. When we trained it in Sweden and validated in Israel, we got very good results. But of course, when we crossed it, trained it in Sweden and validate in Israel, the results were not so good and vice versa. And this is something that you are all familiar with, but it was nice to show it. And again, since I was brought up on model-driven algorithm, I like my student to compare their data-driven results with model-driven results. And this is one example where we compared it. And actually, it shows that the data-driven with the kind of data we use for training do better, but the improvement depends on the level of the rain. With the strong rain, the improvement is less than with a weak rain. So this is it. So now I want to move into the other direction because I don't have time to go through all what P and others did with the contribution to environmental monitoring, but I want to go into theoretical signal processing. And as I say, this may be considered as very specific problems because they are related to this application, but theoretical problems are always nice and they may be applicable to other problems. The first one that I want to mention is the following. When we first got measurements from cellular providers from the network management systems, we didn't get instantaneous samples of the signal level. Instead, they send us two numbers, the maximal and the minimal signal level over 15 minutes. Because that's what they need to monitor their network. So the problem became the general problem of giving only extreme measurements, minimum, maximum, every K samples of a signal. Let's assume it's an IID sequence whose parameters are to be estimated. What is the optimal algorithm and how far its performance is from the maximum likelihood algorithm if you had given all samples. Theoretical question. You can consider it as a compression problem because if you have only two samples, the minimum and the maximum, instead of the whole instantaneous sampling, it's kind of a compression, right? And actually, in this work, we developed a test using a Fisher information matrix approximation for using only the extreme. And we found out that the difference is not so big. And we can get with the extreme, especially with the maximum attenuation, results very close to the case if we had all samples regarding some specific parameters.
That would very much depend on the tail distributions, right? So if you have Gaussian tails and you have a Gaussian distribution, it's going to probably be very different from, say, a Pareto distribution, which is...
We use exponential distribution because this is typical to rain. It is gamma distribution or other exponential distribution.
Yeah, so that's a good assumption. And so
But I must say that this Fisher information matrix with extreme happen to be very useful for this problem. Another problem is a theoretical problem of a kind of Nyquist rate for random sensors. The problem is as follows. Given measurement taken by commercial microwaves in arbitrary geometry, like what you see here, the yellow here, what is the achievable resolution of a reconstructed two-dimensional field? Here, the resolution is a free parameter. I can decide on how big is the pixel.
So,
But the question is, given the way these sensors sample the two-dimensional rain field, what is the size which guarantee that I don't lose or I don't miss any event? So again, this is a theoretical question. And the answer depends, of course, on the rain field characteristic, and on the number and the topology of the links. So we assume that we know the statistics of the random links. They are distributed almost uniformly. The center of the links are distributed uniformly. The length is distributing according to exponential rule, and the orientation is uniform. And Actually, we use compressed sensing technique because what was important about the rain field was the sparsity of the rain field. And we found that we have a kind of a phase transition diagram which can determine what is the area where the reconstruction is possible. And we can actually, given the sparsity of the rain field, we can give an answer to this question. Another theoretical question which I like very much, I mentioned it yesterday over dinner, Al, the kind of sensor that we have in our application are this line sensor. And the operation that this sensor do is approximately taking a line integral over the two-dimensional field, okay? And the reason why we get such a nice result, because we have many of them. But what if we had, instead of them, point sensor, rain gauges? For example, if you put a rain gauge on each base station, okay? Which would give us better results? The line sensor or the point sensors, if instead of each link, I don't know why, it is running by itself. So we studied this problem using a Kramer-Rao bound type of problems. We assumed some parametric model for the rain cell. It can be a Mexican head, Gaussian, or whatever. And we try to estimate its parameter. And this is one example where we compare results if you use only line sensors, only point sensors, or mixed sensor. And generally speaking, with rain cells of small size relative to the density of the sensor network, then the line sensors have an advantage because they cover larger area. But if you go to larger rain cells, then the accuracy of the point sensors is better. And the switching is interesting. So this is kind of theoretical problem. Another problem that we studied was the problem of how to optimize estimation after detection. Usually we are interested in accumulated rain because the accumulated rain is important for flood prediction. And flood is a big issue in many of the application. So for accumulated rain, you need first to decide if the rain started, and then to estimate the rain and to see how it is accumulated. But if you have either false alarm or misdetection in deciding that the rain started, then it influences the error on the accumulated rain. Both directions, right? So one of our students came up with a new measure which puts together the estimation errors and the detection errors. And we have been able to show that if you optimize on this risk function, then it is kind of Pareto optimal. For this problem, I must say that our results are limited for the case where the parameter is positive. It's intensity parameter. So this is a theoretical issue, but it's applicable, or it came out of this problem. And the last one that I want to mention is estimating the spatial correlation of rain field. The spatial correlation is very important, and especially the correlation leg, because it tells you what can you anticipate from measurement in one point about other points, both in time and space. And usually the way spatial correlation is estimated from correlating point measurements. But now we don't have point measurement, we have line measurements. And if we correlate line measurements like what we do here, we get a skewed correlation function. So our recent papers show how you can extract the information about the correlation leg, the real correlation leg for this kind of estimates. So I'm 10 minutes before the end of the time, and I can go to the third part, which is some philosophical general lessons. First of all, you may ask, and somebody asked me during the meetings that I carried today, which were very interesting, is it being operational? I hope that I convince you that it's a great idea, but I must say that it is not really operational yet. And this is interesting to analyze why. Right now, very few national meteorological agencies do use this idea or this technology. I mentioned particularly the Dutch national meteorological agencies and the Swedish one. So they are involved with using this technology. I think Meteo France also joined the efforts lately, but not too many. They need to be open to new technologies, and it's a challenge. But the private sector at the beginning, they were interested in it, but then they give it up. So the private sector is a question, why it is not used by the private sector. What are the major obstacles? There was a question about it. First one is access to measurements, to the data. And the data is controlled, but mostly private cellular companies. Not that they care about sharing it, but at least when they were richer, they didn't care about spending time on weather. I mean, they got a lot of income from communication. So who cares about the other? The other obstacle was to bridge the gap between demonstration and proof of concept, which needs a lot of efforts. And we needed to work hard to gain trust of the relevant community. The people are kind of conservative when you introduce the new technology. So I try to give medals to the different stakeholders. So I give gold medal to the R&D community, because the R&D community indeed became very interested in this topic. There are at least 30 active research groups worldwide. And most of them are working on CML data. And as I said, each group should approach national cellular providers, and they got the data under different systems, and they produce rain maps and they prove its feasibility. But some groups are also looking now on different opportunistic environmental sensor, like, for example, the handset itself. You know that each such smart machine carry on many sensors, temperature and others. And if you have access to this data, then you can gain a lot about the environmental data. And as I mentioned, also satellite is a new source of information. So I give the gold medal to the R&D community. It's nice, we give it to ourselves, right? The silver medal goes to the public sector. I must say that the public sector international organization recognize the potential benefit, especially for developing countries. And some of them initiated and support a project. So there is slow adaptation by national meteorological services, which are also in the public sector, with the encouragement of international organization. And the private sector, very limited success in past initiative. So I give it bronze, but maybe deserve nothing. I don't know. But why? So let me show you some data. This is, for example, a poster from a conference which took place in Seoul exactly 4 years ago, before COVID, before everything. And there were introduction of this technology, and especially rain rate mapping products from different countries and different R&D groups around the world. And you see Netherlands, Germany, Sweden, Czech Republic, which is very active, Italy, 2 groups in Italy, Israel, and most important by African countries like Cameroon, Niger, and Burkina Faso and Brazil. These are developing countries that started to adopt this technology. And as you can see, all of them developed and could produce local rain maps with data that they got from their own cellular providers. This is a photo from a international conference that we had last year in Israel of the R&D community. So there is a community and it is interactive. And this is the most exciting part. Actually, the European Commission, the European Union, they support action which is called COST. COST stands for Cooperative Science and Technology. And exactly a year ago, they started to support a COST action, which is called Open Sense, Opportunistic Sensing. Opportunistic Precipitation Sensing Network, Open Sense, brings together scientists investigating different opportunistic sensors. Okay? And this is an active open network, and if any of you is interested in it, you can join, and maybe not as a partner that they get resources out of this, but at least you can get access to the data, because the first working group was about harmonization of the data that we have in different countries, which is very important. Then we have a working group on methods, algorithms, applications, and others. And here is the link to the webpage of this COST action. As I said, the silver medal goes to international organization. Back in 2015, there was a workshop in Africa, which was supported by, I think, the International World Bank. And in this workshop, we introduced this technology. There were 87 participants in this workshop from 18 countries, including 30 trainees from Africa. And since then, since 2015, they started to use more and more of this technology in Africa, which is a target place. And more interesting, there is a non-for-profit organization, which is called GSMA. It is an organization representing the interest of mobile operations, operators around the world, about 750 of them. And they initiated a project which is aimed into what they call LMIC, meaning low and middle income countries, encouraging the local cellular providers to share their data for the purposes of better weather monitoring in these countries. So this is initiative by a non-profit organization to get access to the data. And indeed, it already produced several papers experimental on this area. And this is my experience with private sector. Actually, very interesting, the big company Ericsson, which controlled at least 50% of the microwave equipment worldwide, became interested in our technology back in 2015. At that time, they realized that the market is changing, and they were interested in a new horizon for different applications. And they came out with a structure which is shown in this slide that I took from them. They say, okay, we are Ericsson and we are in close collaboration with many cellular providers. So we can take responsibility over collecting and aggregating the data. And what we can do is after we do it, we transfer the data to somebody else that will convert the data into weather products based on the algorithms that I mentioned before. And then this weather product can be commercialized to the market. And then we will do some kind of revenue sharing between this company, Ericsson, and the cellular provider. Great idea. I liked it very much. Luckily, in early 2016, 3 young people approached me and they say, we are looking at your technology and we want to found a company over this technology. I said, that's great. And they wanted me to be a co-founder. I said, that's great. Let's be the company that will take this place here. Because we are familiar with the algorithm and we can take the data from Ericsson and make rain product from this. And that was the time this company, Climacell, was founded. But I must say that my colleagues, my co-founders, they was not so excited about being dependent on Ericsson, on one company only. I personally thought that if it will not Ericsson, it will not happen, because then they need to negotiate with each cellular provider separately, which is crazy. So in a way, we split it. They went their way, I went my way a year after. And the first thing that they did, that they took out the cellular out of their logo in 2017 after I left them. And last year they changed their name into Tomorrow or Tomorrow.io. And now they went far away from this technology. And instead they are talking about putting radar, satellite weather in space. So it's a designated equipment, very different. And when you look at it, you say, why people go to a designated equipment instead of using opportunistic data? Maybe the market incentive is to get more investment, and then you need to show more expensive. I don't know. There is a market failure the way I see it. But if I want to summarize what happened over the last 15 years since we started this technology in 2015, this is my summary. First of all, this is definitely an emerging R&D trend. The concept of opportunistic environmental sensing is everywhere, not only in weather, but also in birds and in other technologies. And you just need to start thinking this way, and the sky's the limit. So this is good news. As I showed you, there are several theoretical scientific questions that raise out of this technology, which is also great. There is potential contribution to the public good, like sustainability, developing countries, etc. And maybe I'm too optimistic, but I believe that the concept of integrating communication and sensing is somehow related to the ideas that we raised then. So now they are talking more about technology, not opportunistic, but we did it in an opportunistic way. So I probably don't have the 2 minutes to go over the future, but if you let me, I just summarize it here. If we look at the broader picture, first, the concept of opportunistic sensing of environment, but not only the environment, I see it as exciting emerging field. And it's really important now when we talk more and more about sustainability. Instead of building more and more equipment, you can do a lot with the existing technology. Emerging technology like the 5G bring in new opportunities. The technology is, as I said, opportunistic ISAC, opportunistic IoT. And there are many applications, like in meteorology, where you actually need fusion of traditional measurements with this opportunistic sensing. This item, we talk about the contribution to scientific research. I didn't have time to talk about it, but for example, when we talk about smart cities, the climate within city is very different from the climate around it. There are, the effect of the city on the local climate is significant. But till now, they had no way to measure the intercity climate. With our technology, where you have links on the street level, etc., then you can measure it, and it's a big opportunity. And the last point is referring to the other direction. We have a joint project, BSF NSF is Columbia University, where we use what we know about the effect of weather on communication links to improve communication. Because we can actually predict fading in the communication link network, and if we can predict fading, then we can improve the quality of service of the communication network. So I jumped into the acknowledgement, and this is very important, and it is related to the question which was put before. I put here, and I mean it, acknowledging all these commercial for-profit companies that collaborate with us over the years. They share data, they share knowledge, and they do it for the sake of science. So this is the important acknowledgement part. And this is my last slide. This is the webpage of our research group, and you can find there all the information, papers, presentations, etc., etc. And you are most welcome to email me if you have anything after this talk. I'm here for you. Thank you very much. Questions? I think we can also get questions over Zoom, right?
Jake, is it time for questions?
Yeah, we need to close it. Sorry.
So I have a question.
Yeah.
And that it relates to one of the points you made about why the private companies are not really jumping on this technology. And it would seem to me that part of the problem is that the business model is not yet well understood. And indeed, if you have to depend on the goodwill of a major service provider to get your data so that you can then develop your startup to build in a rain prediction or severe weather prediction type of application, then there's just too much contingencies, right? That could in the way of developing the technology. So
you're absolutely right. That's why I really like the idea of Ericsson, because they took responsibility for the data.
Yeah, that's right. Yeah.
So if you have a third party and their idea, I liked it very much. Because otherwise it is very hard for a private company to, and it's also hard to switch between fields. Mm-hmm. If you are in environment or if you are in communication, it's hard.
Yeah.
So Ericsson idea was they put money on this project, Ericsson, because they were willing to take it further, but somehow they didn't find who will do this part at the end of the day. But the product itself, it became a big market. Weather became a very big market. As you know, all the big companies, IBM and Google and so on, they all are in weather now.
Yes.
So there is a market for weather products. And actually this company, which is now Tomorrow.io, they have many customers now, and they use other sources of designated equipment for measurements instead of using opportunistic. There are many ideas though how to use opportunistic data, like for example, the wiping rate in automatic may tell you also about the rain rate, etc., etc. But the data became a major challenge, and you're absolutely right.
The other question I had was concerning sort of the future when you look at 5G and beyond. Granted, we're probably not going to get to microwave types of wavelengths between handsets, as you said.
They are talking about 24, 28 gigahertz.
Yeah, 39 gigahertz.
Yeah, so that's okay. That's great.
That would be great. But
and if you're talking about stationary points like IoT,
yes, right,
then we are willing to use these links.
Yeah, and dense cell.
Yeah.
So you have the whole concept of massive MIMO 5G. The cells become much denser, so now they can use much higher frequencies without the attenuation problem.
But the problem is with short links, you have other kind of uncertainties and problems, and we study this issue.
Yeah.
But no free meals, that's the trade-off, yeah. But there are many opportunities, especially in cities, because in rural areas, in dense population between cities, everything tend to move into fiber. So you may have some links in rural, and in cities, many links. So it has changed and it is changing. So you're absolutely right. Yes, please.
Yeah, so how computationally intensive is it to do this?
Not really.
Okay,
Because weather phenomena are very smooth. So you have at least 5 minutes between two interesting data points. It's a lot of time, so you can do a lot. And actually, most of them are local. So you don't need the global data to get results. So you have a limited climatological area, and then not really a problem.
where does your data, or like, where do your data labels come from? Because you said you have higher resolution than like the weather radar, so how do you get that?
Because that's the rate that we get from the cellular providers, how they maintain their data.
Yeah, but how do you get the labels? Like, how do you get?
We did it with rain gauges, and with the rain gauges, I think the rain gauges, most of them are every 10 minutes or so. So yeah, we adjusted it. Again, as I said, we are talking about different sphere. It's not communication. The errors are much larger. But most meteorologic are happy with 30% error. This is great for them. So it's and also the rate is much slower. So you can do a lot using signal processing algorithms. I have 2 questions on the chat. Yes, please ask. You want me? No, do I control it? I think you can.
Type, I think you can just type the,
Ah,
where is the,
is it better to type the question or?
can
Are
they
you
speak
able to
over?
hear the chat?
Yeah, should I unmute him? He can unmute himself.
Are you able to
Hey,
hear
you
people
can
in the Zoom
unmute
chat?
yourself.
I think I can hear.
So.
Yeah,
Oh,
It's
okay.
weak, but I can hear.
So opportunistic sensing falls somewhere in between like active sensing, like radar, where objects are illuminated intentionally, and passive sensing, like EO, that uses naturally illuminated, visible, and IR bands. And I'm just wondering, is there any specific characteristic of cellular signals that make them suitable for this type of sensing, or in principle, can any human-generated source of EM radiation be used, like FM or AM radio, or maybe even like shortwave radio that can sense things on the other side of the planet from reflection off of like the ionosphere?
Yeah, it was quite weak, so I hope that I got
Yeah.
it. Can you maybe?
Yeah, I think the question is with the cellular system that offers a really clear channel to do this attenuation estimation, but is it possible to do this with other types of channels that perhaps might have lower attenuation profiles? For example, it was mentioned shortwave radio, millimeter wave, HF radio, and so forth.
Yeah.
And I think the background for the question kind of is, if I can sort of add to it, is that even though you might have less contrast and lower signal to noise ratio, because the relative attenuation at those frequencies is quite small.
Yeah.
If you have many sources,
Theoretically, that
you might be able to
yeah.
compensate for that.
theoretically, this is definitely the case. But when you talk about attenuation, for example, you may get attenuation because of scattering.
Yeah.
Or because of observation, and it depends on the wavelengths.
Yeah.
So the big attenuation that we see with rain is because of miscattering. That's what, and for this we need a millimeter wave or about microwave wavelengths. If you go to a lower frequency, you may have other effects, but as by definition, all signals are affected by the propagation channel. But the question is first the sensitivity, and then also if you have records, if you have existing records of the data. Because for example, television signals, now with the new system, satellite and other VOD and other system, you may have more. But if it was broadcast only, then you have the data there, but nobody log it and record it. So for us, it was simpler to go, as I said, for where it is easier to get results. But theoretically, it's everywhere. But there are, as I said, once you start to think opportunistically, you can get many interesting ideas. For example, the main disadvantage of this technology, that basically you get measurements only over land, not over the sea. So I asked myself, what can you do over the sea? And one idea is that if it is raining, then the rain is kind of acoustic noise for underwater sonar system or whatever. So maybe you can extract information about the rain from the noise in the solar system. So it's just a way of thinking. Once you instead of building more and more and placing more and more and maintaining more and more designated equipment, just think opportunistically. That's my message, my take-home message.
Well, there's a very interesting project that you may not be aware of. It is the Redbox project, where it's a project where people download software to their cell phones, and the software basically records the accelerometer and the microphone of the cell phone, and is able to detect infrasound. So you were talking about acoustics.
Actually,
and they can detect.
do you know the
and
story?
localizer.
Do you know the story from the Second World War? That the German, they could tell the weather in London because the Big Ben was transmitted in real time.
In real time, yeah.
Really? So this is the first opportunistic use of acoustic wave. And then they realized that this is the case and they changed it into recording Big Ben. This is a very nice story. I'm not sure if it is correct, but it's a good one. I have another question online. Who is the ask? Okay, I will read it. Have you observed different behavior with different modulations of the microwave link? Is it possible to leverage frequency-dependent observation to further increase the accuracy, considering that microwave could have much higher bandwidths? So regarding modulation, in all this backhaul scheme, they have a responsive going into lower modulation QAM scheme when the quality of the link is lower. So usually they have two ways to overcome fading. One is ATPC, automatic power control, where they increase the transmit power or the lower the modulation scheme. We looked at the effect of changing the modulation and we didn't get much out of it. There is integration for it, but it didn't add significant information to what we get for the received signal level. So this is one answer. Of course, it adds some, but not significant enough to be cost effective. About the possible leverage on frequency-dependent observation, as I said, the attenuation depends on the frequency. And we have diversity of frequencies. And actually now in many backhaul systems, they put dual frequencies, one in millimeter waves and one in lower frequency to overcome problems that may caused by strong wind, for example. So the diversity is the key point. I'm not sure if I answer your question, but that's the way I understood it. Any other questions? Yes, please.
So on one of the slides, I forget which one, you talk about measuring latency using, you use latency to predict weather events. So I'm wondering, like, like how you're measuring latency? Because I know in like communication networks, a lot of latency is related to like the signal strength, or at least in like Wi-Fi or like TCP protocols, the data rate and then the latency is influenced by the signal strength. So is that what you're going with, or like?
No,
how?
in this specific application, the company that provide us with the measurements, they provide us with, they were very much interested in latency, more than in the signal level. So they measure the latency, and that's the kind of data that we received from them.
Right, I guess my question is like, is the latency coming from that like software level where the communication protocol is slowing down the data rate and then increasing the latency, or like where is this latency coming from?
No, I don't think it's from the protocol. They try to minimize latency due to the processing. It's physical latency due to the propagation of the signal over the link.
Okay.
And this is, that's what we are interested in. And this is affected by the humidity in the air. It's actually influence the propagation rate.
Great. Any other questions?
Not online?
Not online.
Here, no.
If not, thank you so much for a great talk.
Thank you.
Very interesting.
Should I turn off the Zoom?